Welcome again, everyone. In this video, we are discussing the first three questions of activity 2.3, which is based on system of linear equation with invertible coefficient matrix. That means if you are given a system Ax equal to B, so in this system, the matrix A, which is your coefficient matrix, is invertible. So before delving into the questions, let's check some theory. So the matrix A is invertible if and only if it is non-singular. That means the determinant of the particular matrix must not be equal to 0. So there are two conditions. First, it must be a square matrix, and second, its determinant must not be equal to 0. So if both the conditions are satisfied, then we can define the inverse of the matrix as 1 over determinant of A times the adjoint of the matrix A. Now there are multiple ways to find the inverse of a matrix, and there is one more way to find using the elementary row operations. So if you are given this augmented matrix A pi pi and you perform a series of row operations such that A becomes the identity matrix, then by using the same elementary operations on I will result in B, and that particular B is going to be the inverse of your matrix A. So we'll see that with the help of an example here in the very first question. So the question says we need to match column A with column B. So we'll be using the same method to find the inverse of the matrix A1, A2, and A3 if it exists. So this is true if and only if A inverse exists. That is, determinant of A is not equal to 0. So first let's start with A1. So A1 in this case is given by 1, 2, 3, 0, 2, 3, and then 0, 0, 3. So here what we have done is we have written the matrix A1 and we want to find the inverse of the matrix A1. But before that, we'll have to check whether the inverse exists for A1 or not. So to do that, we will find the determinant of A1, and since it is a lower triangular matrix, then its determinant is just equal to the product of the diagonal element, which is 1 multiplied with 2 multiplied with 3. That gives us 6, which is not equal to 0. Thus, A1 is invertible. Now, once it is known that A1 is invertible, we can find the inverse of this particular matrix. So we have seen that if we start with this matrix A1I and perform a series of elementary row operations such that A1 becomes the identity matrix I. Then using the same elementary operation on I will result in B, and this particular B is going to be the matrix A1 inverse. So let's get started. So here we have the matrix 1, 2, 3, 0, 2, 3, and 0, 0, 3, and we are going to augment it with the identity matrix of order 3. So 0, 1, 0, 0, 0, 1, 0, and then 0, 0, 1. So we are going to perform some operations here. So what are the operations that we can perform to make this matrix the identity matrix? So I have written some operations over here. First, we are going to perform this operation in R2, which is half times of R. Then what we are going to do is we are going to do R3 is 1 by 3 times of R3. So what would happen now? It will become 1, 0, 0, 1, 1, 0, and then 1, 1, 1. The same operation if performed on this I, it would result in 1, 0, 0, 0, half 0, and then 0, 0, 1 by 3. Okay. So we are going to perform next set of operation here, which is R3 minus R2. So once we do R3 minus R2, what we will get? We will get 1, 0, 0, 1, 1, 0, and 0, 0, 1. And now doing the same here will give us 1, 0, 0, 0 half 0, and 0 minus half 1 by 3. And then one last operation, that is R2 minus of R1. So that would give us 1, 0, 0, 0, 1, 0, and 0, 0, 1. And using the same operation here will give us 1, 0, 0, minus 1 half 0, and then 0 minus half 1 by 3. So this matrix A is now converted into the matrix I, and this matrix I has been converted into this new matrix, and this new matrix over here is going to be the inverse of A1. So we'll check that whether it is present in the options or not. So 1 minus 1 0, 0 half minus 2, and then 0 0 1 by 3. So yes, this is the matrix. So B2 is equal to A1 inverse. That means A matches with. Now we are going to perform the same operation on A2. So here let's write A2 first. So A2 is 1 0 0, 1 2 0, and then 1 2 3. So A2 is a upper triangular matrix. So again we can find the determinant of A2 as 1 times 2 times 3, which is the product of diagonal element, which is equal to 6, not equal to 0. So again A is also non-singular. So A2 inverse also exists. Now let's perform the same operation with A2 to find its inverse. We are going to write 1 0 0, 1 2 0, and 1 2 3, and then the identity matrix over here 1 0 0, 0 1 0, and 0 0 1. Okay. So the first operation that we are going to perform here is R2 going to half of R2, and similarly R3 being 1 by 3 of R3, that is dividing R3 by 1 by 3 and multiplying R3 with 1 by 3 and multiplying R2 with 1 by 2. So let's do that. It will result in 1 1 1, 0 1 1, and 0 0 1. And here this will give us 0 1 0, 0 half 0, and then 0 0 1 by 3. Once it is done, we can use this operation where we are saying R1 minus of R. So if we perform this, we will get 1 0 0, 0 1 1, and 0 0 1. And here it will become 1 minus half 0, 0 half 0, and 0 0 1 by 3. And now to make this an identity matrix, we will just say R2 minus of R3. That will make it 1 0 0, 0 1 0, and then 0 0 1. And this will become 1 minus 2 0, 0 1 by 2, and minus 1 by 3. Then I have 0 0 1 by 3 over here. And the matrix is my A2 inverse. So I just need to check the options now. So it is 1 0 0 minus half 0, minus half 1 by half, 1 by 2, and 0, and 0 minus 1 by 3 and 1 by 3. So B3 is my A2 inverse. So that means B will get matched with 3. And now coming to A3. So let's write A3 over here. A3 is 1 2 3, 2 3 5, and 3 4 7 7. Yes. Okay, so it's not a triangular matrix, so we'll have to find its determinant. So to find its determinant, what I'm going to do is I will perform this operation, that is R3 minus of R2 minus of R, because here I can see that R3 is basically equal to R1 plus R2. If you add these two rows, you will get R3. I'm going to perform this operation where I'm going to subtract both R1 and R2 from R3. So that will give me determinant of A3 as 1, 2, 0, 2, 3, 0, and 3, 4, 0. That means since I have a 0 row over here, determinant of A3 is equal to 0. That means A3 is non-invertible. So A3 inverse doesn't exist. So yes, option 1 matches with C. So this is all about question number 1. Now let's move on to the question number 2. So question number 2 and question number 3 uses a common data where we are given a system, and in the question number 2 we have to find the value of A inverse and also what is the adjoint of the matrix A. So what is adjoint of a matrix? So adjoint of the matrix is basically the transpose of the cofactor matrix. That means if you have C11, C12, C13, C21, C22, C23, and C31, C32, C33. If this is your cofactor matrix, then the transpose of this matrix is going to give you the adjoint of A. That means it is just C11, C12, C13, C21, C22, C33, sorry, C43, and then C31, C32, and C33. Okay. So to find the adjoint of A, we'll have to find the cofactors. So first let's find the value of C11. The value of C11 is minus 1 to the power 1 plus 1 times the matrix obtained by eliminating the first row and the first column of the coefficient matrix A. So if we eliminate this row, this column, we are getting this small determinant 0, minus 1, 1, minus 1. That would give us minus 1 to the power 2 is 1 itself. It is 0 minus of minus 1, which is 1. Now similarly, we can find the value of C12 as well. So C12 is equal to minus 1 to the power 1 plus 2 times the determinant 1 minus 1, 0 minus 1, 1 minus 1, 0 minus 1, which is equal to minus 1 times of this minus 1, which is again equal to 1. Then comes C13. It is minus 1 to the power 1 plus 3 times of 1001, 1001. So it is just minus 1 to the power 4 times 1, and this determinant is equal to 1. Now comes C21. C21 is minus 1 to the power 2 plus 1 times this determinant, which is given by minus 1, 0, and 1 minus 1. Minus 1, 0, and 1 minus 1. So it is equal to minus 1 times of 1 minus 0, 1. So it is basically equal to minus 1. Moving on to the C22, it is minus 1 to the power 2 plus 2 times of 2, 0, 0 minus 1, which is 1 times of minus 2, which is equal to minus 2. And then C23 is equal to minus 1 to the power 2 plus 3 times of this matrix. Eliminate this row, this column, and the determinant of the matrix 2 minus 1, 0, 1. 1, 0, 1. It is equal to This is going to give us minus 1 times value of this determinant is 2 minus 2, that is 2, and it is equal to minus 2 here. And now we are just left with C31, C32, and C33. So C31 is minus 1 to the power 3 plus 1 times of determinant. Eliminate this row, this column, minus 1, 0, 0, minus 1. 1, 0, 0, minus 1, which is equal to, this is minus 1 to the power 4, which is plus 1, and it is again positive 1, so it is going to be 1 itself. Now C32 is equal to minus 1 to the power 3 plus 2 times of the determinant 2, 1, 0, minus 1. 2, 1, 0, minus 1. So it is equal to, let's check it again, it is 2, 1, 0, minus 1. Yeah, that's fine. So minus 1 times of minus 2, that will give us 2. And then C33 is equal to minus 1 to the power 3 plus 3 times of this determinant, which is equal to 2, 1, minus 1, 0. And it is minus 1 to the power 6, which is positive 1. And it is 0 minus of minus 1, which is equal to 1. So now we can write adjoint of A here, which is equal to C11, C12, C13. So 1, 1, 1, 1, 1, and then comes minus 1, minus 2, and then comes 1, 2, 1. So this is my adjoint of A. So now let's check whether it is present in question 2 or not. Yes, this option is correct. The second thing is to find the inverse of the matrix A. So once we know the adjoint, it is very easy to find the value of inverse. Why? Because A inverse is given by 1 over determinant of A times adjoint of A. So let's find the value of determinant of A first. So we can do it here as well. So this is A, so determinant of A would be given by 2 times of 0 minus 1, 1 minus 1, minus of minus 1 times of 1 minus 1, 0 minus 1. Second right thing is 2 times of minus of minus 1, that is positive 1, plus minus 1. So the determinant of A in this case is just 1. So since the determinant of A is equal to 1, I can write A inverse as A equal to adjoint of A, and adjoint of A in this case is given by 1, 1, 1, minus 1, minus 2, minus 2, and 1, 2, 1. We did this because determinant of A was equal to 1. So yes, this is our answer for the question number 2. Now moving on to the question number 3, that says, what is the value of x1, x2, and x3? So here we have the system Ax equal to b with us. Now if you want to find the value of x such that A inverse exists, then how do you find the solution of this system? So in this case, you can just pre-multiply both the sides with A inverse. So what will happen? It will become A inverse times B. A inverse times A will give you I is equal to A inverse times B. And I times X is just X equal to A inverse times B. Now, what is your A inverse? That we have done in the last question as well. So it is 1, 1, 1, minus 1, minus 2, minus 2, and then 1, 2, 1 times of B. B is a known vector. So we can pick the B from here, which is 3, 3, 3, 3. So now if we solve this, we are getting 1 times of 3, that is 3, minus 1 times of 3, that is minus 3, and then plus 2. Then it is 3 minus 6 plus 4, and then it is 3 minus 6 plus 2. So it is equal to 2, 1, and minus 1. So this is your answer. So your x1 is equal to 2, your x2 is equal to 1, and your x3 is equal to minus 1. So x1 equal to 2. So it is wrong. X2 is equal to 1 and x3 is equal to minus 1. So with this, we have completed the first 3 questions of activity 2.3. We'll see you in the next video. Till then, bye.